I extend a very warm welcome to this technical talk. So it's a part of a talk series called as TEAMS, stands for Talks on Renewable, Empowering Earth and Sustainability. So this talk is part of this center. Before I introduce the speaker, I request Dr. Dheeraj Patil, faculty at Harvard, to introduce the current activities of the center and to talk about the center. So, Dr. Dheeraj.
Thank you, Professor Arpan. I will share my screen, Professor Christos.
Yeah, do I need to stop sharing?
No, it will come, my screen. Okay. Is my screen visible?
I don't know because I'm looking at mine. Yeah.
Yeah?
Yeah.
Okay.
Yeah, visible.
Okay, thank you for asking me to present about this center. The center is a global center of excellence in affordable and clean energy, which is we abbreviated as GCoE-ACE. And affordable and clean energy is one of the sustainable development goals. That is sustainable development goal number 7 from United Nations. So center is committed to provide the laboratory facilities, upskilling, research and development facilities, outreach and talks. Out of one of the the talk series is we call it Streets Talk, which is what we are gathered today. Also, center is committed to have hackathons and challenges, innovation support and incubation support, and the grassroots implementation and field level experiences, field deployments and field mentorship and guidance. The center is established with the support of Honeywell, as well as Office of Principal Scientific Advisor, Government of India, and our grassroots implementation partner, Selco Foundation. Currently, the center is establishing the laboratory equipments in testing and measurement, fabrication and prototyping, skill development and outreach, as well as R&D laboratory facilities in power electronics. We are also coming up with model clean energy village in the nearby village so that we can do the field test, and we call this as a field test lab. The center got inaugurated in January 2022 by the Professor K. Vijayaraghavan, the presence of Mr. Vinayak Chatterjee. And we have gathered here for these 3 talks, which are talks on renewables, empowering earth and sustainability. We had series of talks from Dr. Harish Hande on poverty, sustainability and technology, by Mr. Ramakrishna YB on the national biofuel policy and initiatives, by Professor Soni Kar Narayan from University of Cambridge on the functional nanomaterials, by Dr. Sara Barbara on the wind energy, Professor Venugopal on the ocean renewable energy sources, Professor Lee on the high performance cooling techniques, and Dr. Prakash on water and crops. Today we have speaker, Professor Christos Markides. He is from Imperial College London, and we will be eager to hear from him. The center is currently inviting problem statements, and this is an open problem statement. Initial phase has been completed by 15th of May, and we have a second invitation on. And this problem statements would be in the area of electricity. If you have been hit by adverse impact, adversely impacted by the lack of access to the reliable energy source, then you can participate in these problem statements for the center. Center is also inviting innovators and entrepreneurs through Catalyze Tech. If you have a solution for some of the problems and ideas, then you can pitch those ideas, and we can take the ideas from the idea to prototype and through the incubation cycle. So center is open for these ideas as well. Lastly, the center is also having a competition on poster making and competition in Indian languages. The theme for this poster making and slogan competition is on affordable, clean, renewable energy for protection of earth and environment. It's opened on 20th May and closes on 3rd of June. The results will be on the Environment Day, that is World Environment Day on 5th of June. So this is the brief about the center. So thank you again, and I hand it over to Professor Arpan.
Yeah, thank you, Dr. Thinesh. So that's my immense pleasure to introduce the guest speaker, Professor Christos, for the talk, high efficiency integrated hybrid solar heating, cooling, and power systems for distributed applications. So Professor Christos is a professor of clean energy technologies, head of the Clean Energy Process Laboratory, and leads the Experimental Multiphase Flow Laboratory, which is the largest experimental space of its kind at Imperial College, London. He is also, amongst others, editor-in-chief of Journal Applied Thermal Engineering, a member of the UK National Heat Transfer Committee, and on the scientific board of the UK Energy Storage Supergen Hub. He specializes in applied thermodynamics, fluid flow, and heat and mass transfer processes as applied to high-performance devices, technologies, and systems for thermal energy recovery, utilization, conversion, or storage. His research interests include heating, cooling, and power, and in particular solar energy and waste heat recovery and conversion in heat-intensive industrial applications. He has published about 300 journal and 350 conference papers on these topics. He has won Markides Donald J. Brown Outstanding Paper Prize in 2016, GCoE-ACE Global Award for Best Research Project in 2018, the Engineers Without Borders Chill Challenge in 2020, and received the Imperial College President's Awards for Teaching in 2016 and Research Excellence in 2017. I now invite Professor Markides to begin his talk, and also request him to please share your screen. We would like to inform the audience, if you have any questions, you can post them in the question and answer box. Okay. So over to you, Professor Christos.
Thank you very much, Arpan. I'm just trying to resume my presentation. Can you just confirm that you can see my screen?
Yes, I can see your screen.
All right. Thank you very much for the introduction. I won't spend too much time, therefore. Just very briefly to say that, yeah, we have sort of developed a bit of an interest amongst a lot of other things on solar conversion technologies. And I'll discuss a little bit the research that we've been doing in this kind of space of hybrid systems. I wanted to say I just have two very quick slides to present the group. Because I felt it's kind of useful to try to give a context to some of this research that you're going to see. So this is us. We're based in chemical engineering. This is sort of the chemical engineering department on the left-hand side at Imperial. We tend to try to cover aspects that go from, let's say, more fundamentals, materials, new fluids, coatings. You'll see some of that. All the way to the technology level, device level, right? And then all the way to kind of the system assessments. You'll hear a lot of people talking about whole systems modeling, national infrastructure modeling. Of course, we don't do all of it, but we try to work with various other groups to kind of try to span this range of activities. Okay, so what I'll try to do today is kind of show you a little bit of everything. Okay, so there's not enough time to go into details, but I think I will try to kind of tell you a little bit from the fundamentals, let's say what we're looking at, a little bit at the device level, the collector design, and then a little bit at the highest level of, okay, let's model the system and see what potential it has and so on. So this is really a very, high level snapshot of the group and what we try to do. So there's a lot of activity you can see here. I'm just going to be talking about that one bullet point with the arrow that you're seeing here, right? So we have a lot of interest in solar energy in particular. There are other things going on in the group. People who know me who are on the call will know that we're sort of active in other things. And if people have an interest and want to discuss anything, even outside of what I've presented today, please reach out. My email is on my slides, first slide, last slide. Reach out to me. I'm very happy to discuss anything. Okay, so I usually start this presentation by telling people what I'm not going to talk about, so we can focus a little bit the discussion. Not, by the way, not because this is not interesting or important. It's just that it's not specifically the focus of what I'm going to be discussing today. You will know and you'll have seen this kind of large scale, right? What you would call sort of centralized power station scale, right? Solar technologies for power generation. You'll be very familiar with photovoltaic, so PV farms, people refer to them as large-scale PV, right? With meter after meter after meter, right, over large areas of PV panels. You'll also have seen, so this is the bottom right-hand side of this slide here. You'll also have seen, and you'll know of what's called concentrating solar power, right? There are various versions of this. This is called a tower. So you have a field here with reflectors which reflect light onto a tower, a central tower. There's, relatively high concentration, right, at high temperatures, and you drive a thermodynamic cycle which basically generates electrical power. Both of these, there's not a lot of time to go into the details, but both of these have experienced very significant cost reductions over the past 10 years or so. You can see on the left-hand side for both PV, right, and CSP, what kind of cost reductions it's a factor of 10, right? We've had over the last 10 years, to the point where you can see that these technologies are now competitive with fossil fuel plants. Okay, so there has been a lot of work on this. There's a lot of interest in this. These are very important technologies, but we're not going to be looking at large plants like this. Okay, we're going to leave them out of our discussion. And as I said very quickly, it might have been possible to say that these types of technologies were expensive 10 years ago. But if you look at plots like this, then it's very difficult to sort of continue to argue today that technologies of this type are expensive, especially given the cost reductions that we've experienced. You're seeing here, I'm giving references, by the way, in case you want to explore all of this stuff, but I'm giving here unsubsidized, right? Be careful. So, some people say, oh, yeah, it's cheap, but that's because it's subsidized. No, this is an unsubsidized levelized cost of electricity for solar PV, and you can see how quickly these prices have dropped, right, in the last 10 years. Okay, so what are we talking about if we're not talking about that? Well, we're talking about systems, and you'll have seen in my presentation titled as the word distributed. What distributed really means is kind of smaller scale, right? So smaller things, not tens or hundreds of megawatts, right? We're talking now of anything from a few kilowatts. So it could be like an individual home, right, up to maybe a few hundreds of kilowatts. So these kind of smaller systems for mini grids, neighborhood scale, big buildings, small, a small community type thing. So there's still a range of you can see here, a range of power outputs, but you're also not going up to sort of power station scale. So we're talking about these kind of smaller scale systems, but also there's one further important characteristics of these kind of distributed applications, which is that they tend to be closer to the end user, right? So we're not talking about going into the desert, miles and miles away from anyone and just building this massive plant, okay? We want to be closer to the user. And if you're going to go closer to the user, then there are roads, right? There are buildings, there are all sorts of obstructions. And what this means is that you don't have the infinite flexibility to just put your mirrors anywhere, right? And get very, very high temperatures. So here, you also have the further characteristic, not only that your systems are smaller in terms of their power generation capacity, but also you cannot get sort of the high concentrations that you would get from, these types of parabolic trough or solar tower type systems, right? That you could if you just had vast areas of land, flat land, and you're just placing your mirrors nice one after the other, right? So you don't have that flexibility. So the temperatures are also lower and the power capacities are below. So that's what we're talking about today. And the question is, well, what is available already, right? Well, I mean, you'll know and you'll have seen small scale kind of PV systems on people's roofs. This is a very, very nice technology, highly optimized for electrical power generation from the sun, relatively cheap. I say relatively again, as I said, the costs have dropped a lot. So its job is to convert sunlight to electricity, right? Only. And you'll also be aware of what is called solar hot water or solar thermal systems, where you have, this is again just one type. There are many types. These are called evacuated tube collectors. There are flat plate. There are different kind of designs. But the basic idea is that you have some kind of collector, right, that captures the sun's energy and converts it to a thermal output. So you can heat up water, you can store it in a tank for later use, right? So these are two existing, mature, with very, very large global markets technologies, right? There's still some nice research that's going on both fronts, but they're mature technologies, right? And they've existed for many, many decades. And the question is, well, okay, fine, but a house doesn't only need electricity, and it doesn't only need heat or hot water. Is there a way for us to get multiple energy vectors, right? Because we need both hot water and electricity. And the answer is, well, yeah, you could simply just go and buy both systems and put them side by side, right? So you can put them on the roof, and one would give you hot water and one would give you electricity. But then there's a kind of a follow-up question, which, okay, fine, but is there sort of a smarter way to do that, where we maybe integrate the two things into one, right? Because if you really think about it, they both just sort of take sun and then they deliver two different energy outputs. Is there a way to kind of do that job from the same collector area? And the answer is yes, sure, there is. And this technology also has existed for many years, but it's not. It is technologically mature, but not commercially mature. It's a very, very small market. Most people, actually, if you go and ask like normal people, they might not even be aware that these exist, but they're called hybrid PVT collectors. Hybrid PVT collectors basically take sunlight, deliver a thermal output and an electrical output. So they have cells, PV cells. So in that way, they're similar to PV, right? But they also have, you can see some pipes sometimes. So they have some kind of coolant which flows. And then this coolant basically gets heated up by the sun's energy, right? And that's where the thermal output comes from. So that's really nice. It's a nice option, right? To be able to install just one thing on your roof and to be able to get both electricity and heat. Great. Now, where does the motivation for this kind of PVT collector come from? Or what would be the advantage, let's say, of having a PVT collector, right? As opposed to putting side-by-side PV and just a straight solar thermal system? Well, of course, okay, maybe there's space savings, that's one, but is there anything further to that? This is a plot of, it says power, but actually you can just think of it as efficiency. In fact, you can look at it as a normalized efficiency relative to the maximum efficiency that you would get from a cell at 25 degrees. That's why all these lines pass from this point number 1, right? So this is the efficiency change as a function of the cell temperature for different types of cell photovoltaic materials. You can see amorphous silicon, some thin film technologies, you can see crystalline silicon, and so on and so forth. I mean, you can pick any one of these that you want. The most common one is this silicon down here, crystalline silicon. You'll see that if you pick crystalline silicon and you're sort of taking your panel and you're putting it on the roof and it's a nice sunny day, right, nice and hot, you can easily hit, by the way, 70, 80 degrees on these hot days, okay? So if you do that, then you'll notice that the efficiency, right, can actually drop very significantly. I mean, you're off the chart on this plot. You're probably losing 20%, 25% of your generating capacity simply because these cells are getting hot. Okay, this is the main kind of takeaway from this kind of plot. It's irrespective of the technology that you pick. Yes, some photovoltaic materials suffer less from this than others, but they all suffer from this. So the question, of course, is, okay, this slide kind of presents a problem, right? Then the problem is, well, if your cells are running hot, which they will be running hot exactly on the day that you're expecting to generate more power, right? Because when it's sunny, it's also hot, and that's when you experience these kind of significant losses in power generation. Well, yeah, but it's also kind of telling you that there's a solution here, which is, well, can we just cool them down, right? So can we go from up here back up and to the left and recover some of that efficiency, right? So this is where this kind of idea of not just splitting them and having them as separate systems, right, but kind of combining them might have some additional advantages, okay? So can we use the fact that we have a coolant to cool the cells down? And as I said, we're far from being the first to propose this. So this is a technology that has existed in terms of conventional PVT designs for many years, decades, in fact. And you can see different types of designs out there which already exist. You can see on the left-hand side something called an unglazed design. You can see on the right-hand side something called a glazed design. Glazing really is just a fancy word for a glass cover, okay? And it's similar to solar thermal, so you put glaze or glass covers to improve the thermal performance of your collector, okay? We will see that this addition of the glazing layer to improve thermal performance comes at a penalty in a minute. But, you know, for now, let's just kind of focus on the fact that, you know, you might have them covered, you might not have them covered, but underneath, right, there's the same thing going on, which is we have some cells, we glue the cells onto something with a very, very high thermal conductivity, ideally some kind of copper plate. And underneath the copper plate, we have some arrangement. There are many, many different designs, right? You can imagine, but basically there's some kind of flow channel, right? Where you pass water or some other fluid. Most of the time it's water. And then what you want is you want a very, very small thermal resistance between the water flowing, right, and the cells. And this allows you to pull away a lot of heat from the cells and to cool them down, okay? And this is what really cools your cells. It's this water flowing, which removes heat from the cells, keeps the temperature lower, and therefore improves your electrical efficiency, okay? Great, so we have this kind of design. This is the conventional design. But there's an issue. I mentioned it very briefly, but there's an issue. And this is a plot by one of my students. It's actually getting a little bit old now, from 2014. What she did is she went and found companies which are manufacturers of PVT collectors. And she found different designs of different types of collectors, and she plotted them. This is the thermal efficiency versus electrical efficiency. I know it says output, but it's basically, an output for always an input of 1,000 watts per square meter. So you could take all of those and divide them by 1,000, and you just be getting thermal efficiency and electrical efficiency. And what you'll find is that, you know, these are just different designs by different manufacturers, and somehow there's some kind of inverse correlation, right? There's something very strange that happens, which is that you can clearly see that whenever a manufacturer tries to kind of design a panel, right, and to get like a little bit of a better thermal efficiency, then their electrical efficiency drops. So you're kind of going up that way, right? And whenever they try to design their panel to get a better electrical efficiency, somehow the thermal efficiency drops. So it's almost like there seems to be that the total efficiency is conserved, that you're always sacrificing one to gain the other, or sacrificing the second to get the first one, right? So that somehow you can't win. There's no win-win. It's like win-lose or lose-win or something like that. There's a trade-off, okay? And this kind of motivated us, right? Is there another way to avoid this kind of conventional design and to kind of get a benefit of both? And we'll come to that in a minute. But before we get to that, I wanted to say that, you know, when we are dealing with heat, let me just go back. When you're dealing with heat, so this thermal output, unlike electricity, it's not enough to just keep saying, oh, well, I'm getting more heat. Yeah, because heat, of course, we can talk about second law of thermodynamics and go into details, but let's just say more simply, right, that for the same amount or quantity of heat, the temperature of that heat matters, right? And the higher the temperature, even for the same amount of heat, the higher the temperature, right, the more useful things you can do with it, okay? And you can see here clearly a plot which shows you that, well, you know, if you're at heat at very low temperatures, there are very few things you can do with that heat. Whereas if you go to higher and higher and higher temperatures, you can do more and more and more things with that heat. So it becomes more valuable, more useful. So when we're talking about thermal energy, we don't just care about how much of it we can get, but we also care about what temperature we can get that thermal energy at. Okay, so what can we do to try, right, to do two things? And I'll just kind of summarize, let's say, the challenge, right? The challenge is that when we try to design PVT collectors based on conventional design principles, we end up, first of all, with a trade-off between thermal and electrical efficiency. So every time we try to make something, let's say, better thermally, we lose electrical efficiency, right? First. But there's a second one, which I kind of alluded to already, which is that in a conventional PVT collector, in fact, let me just go back a couple of slides here. So in a conventional PVT design, you remember what I told you is that you're trying to pull a lot of heat away from your cells. And in order for you to do that, you have a very, very small thermal resistance between the cells and the coolant fluid, right? That's, yeah, small thermal resistance, so you have a lot of heat transfer, right? Yes, that's great, but what it also means if you have a very small thermal resistance is that the temperature difference between the thermal output and the cells is very small. Because the two things are, you're getting them very, very close in terms of the temperature. The resistance is small and you're pulling a lot of heat away from the cells, which is great. But that means also that if you want to drive and have a high temperature output from your collector, right, that means that your cells are going to be running close to that high temperature of the thermal output that you need. So you cannot, right, if you want to deliver high temperature heat, you need to be running the cells hot, which, as you know, and we presented just now, is a problem, right? So the question is, can we break the trade-off between thermal and electrical performance? In other words, can we get something which is electrically high performance without sacrificing thermal efficiency? And can we have a thermal performance, right, which is at a high temperature while not causing the cells to be running hot? Can we break this temperature link between the cells basically and the thermal output? The answer is yes, we can do it with something called spectral splitting, which is a different way of designing these types of collectors. And the concept is actually quite simple, right? In this concept, we realize that the cells are not sensitive to all wavelengths of sunlight. They're only sensitive to a part of the spectrum, usually the visible part. So the question becomes, can we split the visible part of the spectrum that the cell is sensitive to, send that to the cells for electrical conversion, and the rest of the spectrum, which the cells are not sensitive to, we don't want to send them to the cells because that's just going to end up heating the cells completely unnecessarily. So we just send them to some separate, like physically and thermally separated component that we call a thermal absorber that we just end up heating. This way we have two parts which are completely separated. They can be at different temperatures. The PV cells can be cold, the thermal absorber can be hot, right? And then we break this link between the temperature of the two parts. So this is called spectral splitting. It can be achieved by a number of ways with filters, right? Optical filters, which can be basically based on principles of preferential reflection, right? So here you can see sunlight comes in, some of it goes through, some of it gets reflected to the thermal absorber. You can see this could be hot now, and this could be cold. They're not connected anymore like they are in conventional designs. Or preferential absorption, right? So here some of it gets absorbed, this can be hot, and some of it flows through. Or there are concepts based on semi-transparent designs, which unfortunately I don't have time to go into today in the interest of time, but what I'm trying to say here is that there are a number of these concepts based on different principles, okay, where there's a filter that either absorbs or reflects different or transmits, right, different parts of the spectrum to different, right, parts of the collector to do different things. You can see here some designs which are relatively old now. I'm giving you also a link if you want to have a look at some of this. You can see these are based on preferential reflection, right? So some of the light gets reflected somewhere, the rest of the light goes through to the cells for electricity generation. So this is kind of spectral splitting designs. Okay, good. That's the background. That's not work that we did. That's a lot of other people that came before us. And so I just want to basically show the results of the work that we've been doing in our group over the years. And as I said before, I want to try to, in the interest of time, okay, I can't go into a lot of details, but kind of go through this journey, right, of different levels of abstraction. So I'll talk a little bit about some more fundamental sort of science developments, right, materials, filters, then go to the component level, maybe talk a little bit about collector design, and then go up to the system level, right? So once we have our collector, right, this collector is going to get installed within a wider system. There'll be control. You sort of operate this in a way to generate electricity, hot water, whatever. So we want to talk about, okay, what's the potential of this type of system to generate energy, useful energy for homes, okay, or other applications. So we just go one step at a time, and then at the end, you can ask many questions you want. So let's start from the fundamentals. I will talk about two things: heat loss suppression and this kind of spectral splitting. Heat loss suppression, why do we want to do that? Well, it's obvious. Heat that is lost from a thermal collector is a direct loss in efficiency, right? So your thermal collector, the job of that thermal collector is to capture sunlight, right, and to deliver useful thermal energy. Any loss from that collector in the form of heat, by convection, by whatever means, right, is a loss in how much thermal energy you can deliver to the end user. So you want to not lose a lot of heat. You want to get that heat and you want to deliver it to an end user. And of course, spectral splitting, how do we actually achieve the thing that I told you before, splitting sunlight and sending it to a different part of the collector and so on. So the first one is a little bit easy. How do we suppress the thermal losses from these types of collectors? Well, there are convection and radiation losses. The convection losses are easy to control. You can do it with a vacuum or heavy gases. There are different sort of solutions there, but okay, I don't want to go into the details of how do we reduce convection, because it's kind of established technology. But I do want to talk a little bit about how to control radiation losses, because of course your collectors get hot. It's a hot surface, right? And that hot surface will radiate heat out back up to the sky. So how can we reduce, right, the emission from that surface? Because any emission from that surface is a loss to us, right? We're losing thermal energy that we could recover and deliver. How do we do that? Well, we do it with coatings, right? Which affect the emissivity of the surface, all right? And if you really think about it, radiation is proportional to emissivity, right? If your emissivity is 0 or near 0, okay? In an ideal world, if you could make the emissivity of your surface 0, then you'd be losing no heat, right? You wouldn't be able to radiate because your radiation is proportional to the emissivity. And if emissivity is 0, then the whole thing is 0. So that's great. But there's a problem, right? Which is that emissivity is equal to absorptivity at the same wavelength. We'll come back to this. And so if you have a collector that you magically, doesn't emit anything, it also doesn't absorb anything. So it's going to be a very bad collector, right? You need to take the sun somehow, right? You need to absorb the sun while at the same time not emitting. So that's a bit of a, let's say, a conflict there, all right? So how do we overcome that? Well, on the right-hand side, we see how we overcome this. What this plots is the energy distribution of sunlight, right? So this is the solar spectrum here. It's a log-log plot. That's why it might look a little bit weird to you. So it's a bit kind of compressed, but you can see in the blue here is the distribution of energy from the sun, which is coming in. And on the red, you can see the black body radiation of something which is the temperature of your cell. And now what's very, very convenient for us is you can see that these two things seem to be separated, right? So the sun is coming in at one wavelength or one range of wavelengths, and your emission from your surface is a different range. So what do we try to do? We try to have coatings that have different emissivities at different wavelengths. So what we want to do is have a high emissivity or high absorption over the wavelengths that the sun is coming in. I want to have a low absorption over the wavelengths where we're re-emitting. So we want to trap the sun, but not re-emit radiation back outwards. There are different kind of coatings for this. There's a nice reference. This is work by my very good friend and colleague Ned Eakins-Dogs here. If you're interested in these kind of emissivity control coatings, please go and have a look. It's an interesting piece of work by his group. Now let's talk a little bit about spectral splitting. First of all, for spectral splitting, the question is obvious, right? It's, well, you've said let's chop off part of the spectrum and send it to the cells, right? Well, which part of the spectrum do we chop off, right? Which are the boundaries, the low and high, let's say, limit, right, that define which bit of the spectrum is going to get chopped and sent to the cells. Unfortunately, again, I'm sorry, I don't have time to go into the details of how this is done, but I'm giving a reference down there. And there are ways, right, to decide which part of the spectrum gets chopped off. The short answer is it's impossible to answer this question unless you're able to define the relative value of electricity to heat. Right? So there's a weighting factor that we defined in this paper, which defines the relative value of electricity to heat. And depending on the relative value of electricity to heat, these bands or this kind of range changes and shifts, okay? And depending, of course, if you were able to pick right, a value for this W, this weighing factor, right? And then you pick your photovoltaic material, then maps like this, which you can find, right, in this reference, can tell you, right, which two wavelengths, right? So which two limits here will define the range within which you need to chop off the light and send it to your cell. So we have a way, let's say, of deciding, right? We have maps that tell us for a given photovoltaic material, depending on the value of heat and electricity, what the range of spectral splitting is in an ideal world. But how do we achieve that? Well, there are many people working on different ways to do it. One is through the use of nanofluids, because nanofluids, well, they've experienced a lot of interest in terms of heat transfer enhancement. But now we're not talking about heat transfer enhancement, right? We're just talking about the ability of particles to absorb light. So it's an interaction with light. And you can imagine different materials, different shapes, sizes, all sorts of things. And all of these will affect bands of absorption. And of course, you can use nanofluids to as optical filter for spectral splitting. You can have these particles in as a sort of in a liquid, in a base fluid. It's called this kind of nanofluid. A suspension, really, is the technical term for it. I don't like nanofluids, not because there's anything, in terms of the science of it, it's very nice, good science. But in practical applications, they have some challenges. The particles can get stuck in different parts of the system. They can agglomerate, they can separate. There are sort of problems there that people are working on. So fine, I mean, while people are working on trying to kind of overcome those problems, I kind of take the view, well, okay, why don't we use liquid phases, right? So use the molecules rather than particles. We use the molecules themselves to absorb. And as you know, for example, water, right, which is a pure liquid, it's not a particle. It's a pure liquid phase, but it is a molecule and it can absorb infrared. So just like water can absorb certain parts of the spectrum, other molecules and other liquids can absorb in other parts of the spectrum. So we're working on a way of kind of selecting different liquids or mixtures of liquids, right, to absorb in a particular band of the spectrum for this kind of spectral splitting. Hydrogels are very interesting, and there are something called luminescent downshifting. That's also a very nice sort of area of work. What's going on here is that, so far we've sort of been treating light as something passive, right? So yeah, sunlight comes in, it's distributed over a range of wavelengths. We can take some wavelengths, we can send them somewhere else, whatever. But there's also something else that you can do, which is you can actually shift energy. So you can take photons, which are in some part of the spectrum, and you can, take them to another part. And you can see here on the right-hand side something called redshifting, right? So you take some photons, which were, so there's this blue, and you take some of them which were in the UV and you shift them into the visible. And you can imagine if you start playing tricks like this, then you can increase the amount of photons which are in the useful parts that are generating electricity from your cell, right? So there's also some very nice interest in this kind of spectral tuning or shifting, it's called. There are semi-transparent cells, again, where your cell comes first and then it traps some light and then the rest of the light goes through to the thermal absorber. Again, always in these designs, basically what you'll see is that there's a thermal disconnect, right, between the thermal absorber and the cell. Right? So these cells are not stuck onto the module. They're not stuck onto the cell, so that we want to create the temperature separation. But unfortunately, I don't have time to go into this, but there are some designs based on this. So let's go to, discuss a little bit materials aspects. Let's go to the collector itself, right? So to the device. How do we design these and optimize them? And well, as you can imagine, it's the usual, right? So we want models, validated models, and we want those models to go hand in hand with experiments. So I'm showing here some models. In our group, we've used a lot of COMSOL, but also we've sort of got in-house three-dimensional or pseudo-three-dimensional kind of codes for thermal modeling, radiation modeling of these types of collectors. You can see here something called a sheet and tube design modeled in COMSOL. You want things like this, right? So temperature maps, right? In order to understand the temperature of the different cells over the surface to get their efficiency. And of course, these models have been validated, right, against experiments. So we have a lot of modeling work at the collector level, right? We have a lot of testing as well. I mentioned, modeling going hand in hand with experiments. So here you can see on the left-hand side a particular type of collector in which you can see there's a tube and the cells are inside the tube, right? Why do we put them inside a tube? Well, because we use the tube to create a seal and then we pull a vacuum. So that's basically reducing convection losses. And then the other thing you can see is that the cells, so there are two tubes, and the cells on the right-hand side look blue, and the ones on the left look a bit greenish yellow. The difference is basically that the cells on the left-hand side, right, so these ones here, we've coated them with this magic coating that I told you before, which happens to be ITO. And the idea of that coating is that it's an emissivity control, right? It's there for emissivity control purposes. What it does is it can absorb the sunlight, right? But it has a lower emissivity at the wavelengths where your cells will start re-emitting heat back out. So it's trying to suppress radiative heat losses. And so these are tests at the lab scale. So this is these are not outdoor tests. These are tests inside a solar simulator, trying to prove, right, this concept that, well, you know, if you suppress convective and thermal losses, right, then you can improve your thermal performance, right? So, of course, because you have less loss of thermal energy, so your thermal efficiency goes up quite a lot. You have a significant benefit. Now, if you look at it very, very carefully, you also see that you have a slight drop in electrical performance, right? So there's still this trade-off. Why? Because it's not a spectral splitting design. All we're doing here is this is a conventional, otherwise collector, right? But it has these heat suppression solutions implemented, right? Evacuation and emissivity control of the surface, so reduce thermal losses, but still there's a small drop in efficiency, okay? So these are tests in a solar simulator. And there are also tests outdoors. Here we do have a spectral splitting collector on the left-hand side being compared directly to a PV panel. So we want to compare the electrical generation potential of the spectral splitting collector versus just having a simple PV panel, right? And what you want to see is basically something like this, right? So you want to see that your solar PV, which has an efficiency of around 15%. So I'm an engineer, so 14.9 and 15 to me are kind of the same, right? Given experimental errors, it's around 15%. So what you want to see is that you have some kind of solution where you don't touch the electricity, you leave the electricity the same, plus you get some heat, right? This is the major advantage, right, of spectral splitting technology or spectral splitting designs. You don't generate heat by losing a little bit of electricity. You want to generate heat by not losing any electricity. You leave your electricity alone, okay? So these are tests, by the way. These are not models, outdoor tests. I showed you the rig. We've been playing a little bit also with solar windows. So here you have a very interesting concept where you trap the sunlight, but it's still transparent. So what it does, it kind of controls the light levels of a building, but at the same time, there's a transparent, a semi-transparent cell in there, so it generates electricity. Plus, you can recover that thermal energy through a flow of water. So here we have a kind of a PVT collector, right? It sort of generates electricity. It generates useful hot water, plus it controls sunlight, so it's a window, okay? And here I'm showing some tests of this. Okay, don't have time to go into it. We have concentrating designs, of course. So far, I've been discussing and showing you non-concentrating collectors. Here, we do a little bit of concentration. As I said, you cannot get high levels of concentration, right, for a system which is on a building roof. So this is all kind of modeling. And I mentioned very briefly, okay, there are semi-transparent collectors, again, at the level of simulation, where, semi-transparent collectors with semi-transparent cells, where you can sort of predict performance for this type of design as well, and of course you can get some results and so on. I don't have time to go into it. And finally, I think this is my last slide. I want to just kind of throw out a very nice project that we have with Tecnológico de Monterrey, which is a university in Mexico, a very good university, and I'm very happy with this collaboration to look at parabolic trough kind of PVT design, right? But it's based on spectral splitting principles again. So here we're going to do modeling, which we're doing in London, and we are going to be testing a design in Mexico. Okay, I want to discuss very quickly a new type of, let's say, concept that we're sort of looking at the moment. We refer to it as PVX. So PVT is kind of obvious, right? PVT is, well, we have the PV to give us electricity. Can we recover some thermal energy as well, right? And we're talking all about this all along my presentation. And the question here becomes, yeah, okay, but can the X be something else, right? Maybe we're not interested in heat. Maybe we don't need hot water. Maybe we need other things, or maybe we need clean water. Maybe we need additional power, fuels, cooling, right? Can we perform this secondary conversion function within the same collector, just like PVT was doing it for heat, but can we do it for something else, right? So we coined this term PVX. So here you can see a PV desalination type of design, a concept if you want, where we have something that kind of looks a bit like a leaf, right, with cells on top, and then there's something below the cells where there's a flow of water, and then that water evaporates, and then we recondense it. So we're sort of desalinating water at the same time as generating electricity from the cells. This is basically what I described. You can see the way that we're doing it. So we're using capillary action. There's no pump in this design. So we're using sort of fibers and hydrogel cells to basically pull water, evaporate it. It's not boiling, it's evaporating. And at the same time, you can see the cell here, right, which traps some of the sunlight. And we've done some tests with this type of concept. You can see here a sort of a design. And we've proven that, okay, the fact that you are, right, causing this evaporation is, number one, causing your cell temperature to go down. So you have a benefit in terms of your electrical generation, right? So we have a design with PVD, if you like, with this desalination or evaporation process happening underneath the cells. And that collector design reaches a little bit less than 50 degrees. If you took the cell without this PVD and you just put the cell under the same, so these are results under a solar simulator, okay? The cell would reach a much higher temperature. It would reach 20 to 30 degrees higher temperature. So that would mean that you'd get less power, right, from your PV. So here you're doing, again, it's kind of like synergistic. It's the fact that you are evaporating. It's not only allowing you to desalinate, right? So you have some kind of water production, right? But on top of that, it's allowing you to reduce the temperature of the cells, right? This is the sort of the concept of PVX, integrated PVX technologies here, PV desalination. So I'm showing you here a little bit of a video on the left-hand side. You can see the water, it's going in and then dripping back down. These are all in the lab, and you can see some results here where this is the kind of just PV. You're getting a little bit more electricity. Why are you getting more electricity? Because you're cooling the cells, right? For the same conditions. Plus you're getting some heat, plus you're getting some water. And this is a nice little figure that one of my students drew, right? So he calls them PV leaf. And so obviously you go from PV leaf to PV tree, which I'm not sure is what you'd want to do. But you can see the concept here, right? It's sort of like, it works like a tree. It doesn't have a pump. It delivers clean water plus electricity. Sometimes I get questions about, yeah, what happens to the salt? So I always make a point of saying that, yeah, there are people that kind of looked at this, and there is some evidence that we can reject the salt at nighttime. So that kind of avoids some problems. I don't have time to go into the details, but we're aware of this. And this is just another project that we have on generating electricity plus fuels. So we're using the heat in this case, right? Not to generate hot water, right? But to generate hydrogen, okay? And then at the system level, I think I have 3 slides, so I'm going to go quickly through this. At the system level, we have a lot of different things, right? We have some kind of collector, right, that can take in sunlight and can generate electricity, thermal energy, or cooling, or clean water, or whatever it is. And then we have very complex systems. We can have storage, we have a demand, we can sell electricity to the grid, right? Plus, we have a control, right, which allows us, you know, given the sun conditions, to maybe change the operating point of the collector. Maybe the price of electricity is changing over the course of a day, right? So there's a lot of complexity in the way that these systems are designed and operated, controlled, if you like. So I'll just show 3 examples. This is the simplest type of example. This is a PVT system where the T is just hot water, which is stored in a tank and used to supply hot water to a home. We've done a lot of work. A lot of other groups have been doing work trying to understand, you know, given some space restrictions for certain homes on the roof, how much heat can we generate and how much hot water, if you like, can we generate? How much electricity can we generate? and what are the economics, right? How much does it pay back? What are the environmental benefits of this type of technology versus some alternatives, right? So there's a lot of work here in different countries, right? Different climates, different demand levels. You can imagine, you can go to somewhere cold. Okay, there's not a lot of sun, but there might be a lot of demand for heat then, right? So there's a sort of an interesting trade-off there. Here's a PV cooling system. So here we're using hybrid PV collectors, but we're using the thermal energy to drive absorption cooling systems. Again, the usual questions are, okay, let's run simulations over the course of a year. Let's look at the economics. Let's look at carbon savings of this type of system. As I said, there are many, many different designs. I'm just showing you one example. And then the most complex type, can we have systems that generate electricity and heat and cold, right? And the answer is yes. Again, is this the only type of system? Of course not. I'm just showing you one example, and the questions are always the same. What is its potential to, let's say, reduce the demand of heating from your end user, reduce the cooling, reduce the electricity demand from the grid, and you have to run annual simulations, and you can see clearly, okay, in different seasons, different months, right? There are different, there's a different generation capacity by the system and different economic benefits and so on. The conclusion of all of this is that PVT, right, generally is a little bit more expensive, of course, because it's more complex than a PV system, but it always generates more useful energy, total useful energy than a PV system. It always have a higher environmental benefit than a conventional system. And so, of course, there's a trade-off here, right? There's a trade-off between, okay, how much do I want to do in terms of my environmental benefit versus, okay, how much money am I willing to spend? And that's really the main conclusion of all of this. Thank you very much for your attention. I hope I sort of showed you a bit of everything, maybe from some fundamentals, a bit of materials, coatings, spectral splitting materials, right? Nanofluids, some other things, to the collector design, right? And then they bid on, okay, what can these systems look like? I'm not saying those are the best systems. I'm just saying there are many, many types of systems, and we want to investigate them. We want to understand their potential. Thank you very much. I would love to answer questions that you have.
Thank you, Professor Christos. I would like to take some questions and answers. So, Dr. Dheeraj, I think you have posted some questions. Would you like to directly ask the question?
You want me to read out? Yes. So, Professor Christos, thank you for the talk. My question is regarding the dust cover on PV collectors. But the dust cover is drastically reducing the efficiency, and cleaning using a good quality water also might be challenging in some of the places. So, are there any self-cleaning coatings which might be integrated with PVT?
Yeah, it's a very good question. So I will say two things to this question. Number one, let's for a moment take the following view. We are discussing, let's say, PVT technology as a competitor to PV, okay? Just for a moment, okay?
Yes.
If we're discussing PVT technology as a competitor to PV, then the problem you described, which, by the way, exists, and in some places it's very, very significant, okay? But if for a moment we say, okay, we just want to compare PVT technology and PV technology, does PVT technology, or PVX technology, I should say, because you might not want the hot water, you might need clean water or something, right? Does it make sense relative to PV? Then the problem is the same in both cases. So if we were to say, well, yes, okay, but your predictions are not going to be as good because there's some dust and whatever, I would say, yes, of course, there would be some dust, but there would be some dust on both sides. So you have one thing which is better than the other or whatever, and yes, they would both go up and down, but it would not change the overall conclusion, right? So if one is better than the other, then adding dust would still mean that the one which is better is still better than the other one. But I would say the following: if we now take a step back and say, well, okay, yes, but we're not just kind of comparing two things. We actually want to know how much useful stuff you can get. And then you're absolutely right. This is a huge issue for any solar technology, right? For any, whether it's a PV panel or a solar thermal collector with dust settling on top, or This is a problem. There are a lot of people working on this kind of, as you say, special coatings. I have ourselves an active project on looking at kind of self-cleaning surfaces. There's some really, really nice things. I can't tell you right now that I'm convinced by anything I've seen, but I think there's a lot of nice progress. I will leave it as follows. So my answer to your point is as follows. It is a very significant issue, in my opinion. You've identified a very significant issue. There is a lot of work going on in this space. Yes, there are some coatings, self-cleaning coatings, designs of collectors, which in some cases are better than others. So, for example, you can imagine a flat plate collector would be worse than, say something which has a curved surface, because a curved surface is a little bit easier, to kind of clean because of the angles and the effect of gravity and wind. I think there's still a lot of work to be done there. So it's a very, very good area to be in.
Sure. Thank you, Professor. So another question that I have is regarding the PV generally operates with multi-point MPPT, that is maximum power point tracking. So with PVT or PVX, do we need to look at maximum or optimal efficiency point rather than MPPT?
Yes, it's exactly the same. You're right. It is exactly the same. You have to operate MPPT, otherwise you would have the same issues that you would have, suboptimal operation that you would have for a conventional PV system. Yes, correct.
So MPPT still will be the part of the system.
Yes, correct. Yeah.
Oh, thank you.
Thank you.
Okay. So there are some questions in the chat box. So Mr. Ravi Prakash says, what is the energy payback time for PVT systems?
The energy payback time the answer is I don't know. I don't look at energy payback, and the reason why I don't look at energy payback personally is that if you're going to go down that route, you have to do life cycle analysis, and when you start doing life cycle analysis, if you really want to look at the overall energy picture, if you want to do life cycle analysis, it becomes highly dependent on where you are. We in my group don't look at this. I'm not saying it's not interesting. I'm not saying it's more important. It's just not something we specialize in my group, right? It now starts to depend on, okay, where do your materials come from? So if you're going to make cells, right? Okay, where did the silicon come from, right? Did you ship it from someplace to someplace else? The error bars on these life cycle analysis are very, very large. But my instinctive reaction is, I would say as follows. Again, we need to compare, right, this technology to alternatives. And if we take the alternative to be a PV collector or PV panel, right, then the energy payback will be shorter. And the reason why I say that the energy payback will be shorter is kind of obvious. The overall efficiency of the system is significantly higher than a PV panel. So a PV panel, you think about it, right, it's between 15-20% to useful energy. So here what you're trying to do is you want to have that 15 to 20% or as close as possible to it, plus you want to have 2 or 3 times that in useful heat. Now you've added materials to it, sure, but you haven't added as many materials as the benefit you're going to get energetically, okay? So my feeling is whatever the energy payback time of PV, this would be significantly better than that. And this is reflected also, by the way, in the environmental considerations. So things like, carbon mitigation potential and so on and so forth. Good question. We don't specialize in this personally in our group. Other people have. I don't know the answer to your question, but I can tell you that whatever it is for PV, this is basically less than that. So a faster payback than that.
Another related question is the hybrid PVT collector commercially viable? And is there any certification organization for this PVT modules?
Is it commercially viable? The answer is it already exists. So if you go onto the internet and you type, I want to buy a PVT collector, right? You already find them. So the answer to, is it commercially viable, is, of course it is. It's already there, right? So we're not, I guess the real question is, okay, look, there are some PVT collectors out there, right? But how economically competitive is it relative to, let's say, PV? The answer is, well, it's more expensive, for sure, 100%. It's more expensive. So what is the point of us looking at this? Well, the point of us looking at this is it's more expensive now. And the reason why it's more expensive now is because what does it do? Well, it generates electricity just like PV does, and it generates heat. So it displaces, right, an additional amount of energy. So you pay more money up front, but you have let's say, a greater reduction in your bills, because you have your electricity bill reduction, and then you have your, let's say, if you're using gas for heating, you have a gas bill reduction. Now, what happens in these cases is actually quite simple. If your gas is cheap, right, then it doesn't make sense to pay a lot of money up front, because the benefits down the line are not going to overcome that initial investment. Or they will overcome them, but they'll overcome them at a slower rate than if you did that electrically, right? If you did the same thing on the electrical side. And that's why simple PV is cheaper in terms of its payback economically than, let's say, PVT, because PVT displaces heat, and if heat is cheap, it doesn't make sense to do it. Or let's say, it's not economically favorable to do it. But relative to PV, I should say, it's still economically favorable, just not as much as PV. So the PV payback is shorter than PVT. And I'll say a very big but here. But if your gas prices start to go up, guess what's happening at the moment? Close bracket. But if your gas prices start to go up, and suddenly the amount of energy that you're displacing is the same, but your gas bills start to go up, then suddenly you displacing the same amount of gas starts to become a better proposition. And at some point, if you're interested, right, in displacing electricity and gas, or whatever other fossil fuel you have, right, if that gets expensive, then we're going to be talking about a different picture, because then you will always have a benefit from these systems relative to PV, because you're only displacing electricity. You're not, right? You're not going to be displaced. I mean, okay, this is a simplification that I'm making, but you see what I'm trying to say. So to answer this question, are they economically viable? They're economically viable right now. I mean, they are commercially viable, they're economically viable, there are people selling them, there are people buying them, there are people installing them. Are they more economically competitive than PV right now? No, they're not, because typically gas is cheaper than electricity, even on a relative basis. But I suspect that if gas prices or heat, the fossil fuel that you use for your heat, start to go up, this will very, very quickly change. So that's my view.
Okay. So there is another question about the waste. The waste from PV and battery storage. So how it impacts the environment.
I'm not discussing batteries in all of the systems that you've shown. Yeah, you've seen today. There are no batteries in the system. You can add them. As I said, there are many, many different types of, the types of system. You can have battery storage. You cannot have battery storage. But remember, I'm discussing applications typically now, right? So I'm not projecting in 2050 what will happen, but typically in our models, we model a system right now, and we use the grid basically as our battery. So if you're over generating, you just sell to the grid. Okay, and if you're under generating, you just buy from the grid. Okay, so you don't need a battery. If you have a lot of penetration, this changes, because you can't always continue to use the grid as a battery. There are issues there of storage at the grid level, but for now, that's not a serious problem in many places. In other places, it is a problem. But so we don't have batteries, so I can't tell you. I don't know, and I'm not an expert in battery storage.
So the waste from PV, yeah.
For PV, it is whatever it is for conventional PV systems. Okay. It's the same cells in the same system. So, and by the way, the people that do this kind of analysis on life cycle energy, life cycle material, and so on and so forth, this kind of decommissioning cost in a good study is included, right? So, I don't know what the answer is, but whatever it is for PV, it's the same for PVT. It's the same area and the same number of cells. And it depends very much. I don't think there's an answer to this question. I mean, it depends on your cell material, right? I mean, are you talking crystalline? Are you talking thin film? Do you have cadmium in there? That's a big problem, right? If you have silicon, it's a little bit easier. So it's a very highly dependent kind of answer. And I don't know. I'm not an expert in photovoltaic waste disposal costs or whatever.
So I think with this, we would like to heartily thank our guest speaker for the trees talk, talk number 8, Professor Christos Markides, for his invaluable time and for a very interesting discussion and presentation. We would also like to thank the audience for the questions and an interactive session. So over to Professor Harton.
Thank you. Am I audible? Hello? Am I audible?
Yes, we can hear you.
Yeah, thank you. So I thank Professor Christos for readily accepting the request and sharing his work and knowledge regarding PVT. I also thank Professor Arpan Gupta for comparing this talk. So in order to strengthen the inclusive technological innovations ecosystem in the areas of renewable energy, energy production, usage, improvements in energy efficiencies, the Global Center of Excellence for Affordable and Clean Energy at IIT Dharwad, along with its partner Selco Foundation, are looking for related problem statements and innovative solutions through an innovation challenge we call as Catalyze Tech. The problem statements may be from sectors such as livelihood, agriculture, allied agricultural industries, resilient micro businesses, built environment, health, education, etc. So I'm putting the submission form for this. Also the submission form for a poster for awareness, for having the awareness about the renewable energy and climate change. This I have both the submission forms. I have put it on Google Forms. I put it in the chat. So please participate. Thank you for participating in this trees talk edition. And thank you again, Professor Christos.
Thank you very much. Thank you everyone for your questions. Very interesting. Have a good day. Bye-bye.